Let's say I have the vector field, let's see, v. The vector at any given point, it's equal to minus, or the magnitude in my x direction is actually dependent on y. So where we are in the y coordinate in the xy plane. Plus, and my magnitude in the y direction is dependent on x. Fair enough. So first let's just chug through this and figure out its curl. So the curl of v, it is equal to our del vector operator cross v, which is nothing but this. And even though this looks like a two-dimensional vector field, we actually have to take the cross product in 3 dimensions, because when you curl is just like torque, and when you like we did the right-hand rule when we studied, well, I hope you watched some of the videos on magnetism and torque, but the torque actually goes in a direction that is perpendicular to both of the vectors in your cross product. So if both of these only have x and y components, your actual result is going to be in the z direction. It's going to be perpendicular to both of these vectors. So when you take the cross product, you still have to do it in 3 dimensions. So I, j, k, partial with respect to x, partial with respect to y, partial with respect to z. The x component is minus y. The j component is x, and we have no k component. This one should be a little bit cleaner to calculate than the last example. So this is going to be equal to, we'll see the I component, let's cross out its column and its row. So it's going to be the partial with respect to y of 0 minus the partial with respect to z of x, right? Minus that. And all of that times I minus, and that is going to be the j component. Remember, you do plus, minus, plus. So minus, and this is the j component. Cross out its row and column. The partial derivative of x with respect to 0, or the partial derivative of 0 with respect to x, actually, minus the partial derivative of z, or the partial derivative with respect to z of minus y. That's its j component. And then finally, plus its k component, row and column. So the partial derivative with respect to x of x minus the partial derivative of y with respect to minus y. I know you can't read it, but that's that minus y there, and that's the k component. And now let's simplify it. I'll simplify it above it. So this term, let's see, partial derivative of 0, well, that's 0. Partial derivative of x with respect to z, well, as far as z is concerned, x is a constant, so that's 0. Partial derivative of 0 with respect to x, 0. Partial derivative of minus y with respect to z, as far as z is concerned, y is also a constant, so that's 0. So all we're left is with this last term. That was pretty straightforward, huh? We just can cross all of that out. And that makes intuitive sense, too, right? Because at least from x's point of view, the rotation is, although it's the rotation, if you think about it, is going to be in a direction, it's going to be in a direction perpendicular to both the x direction and perpendicular to the direction in which it is changing. You could kind of view it orthogonally to its direction of motion, which is y. So it would be in the z direction. If that confuses you, don't worry about it. But if it doesn't, then you could apply the same argument to the j vector. But anyway, let's simplify this. So this is equal to the partial derivative of x with respect to x. Well, that's just 1. Minus the partial derivative of y of minus y with respect to y. Well, that's just minus 1. So it equals 2. So the curl at any point of this vector field is 2. Let's see what this vector field looks like, and let's see if that gives us if our intuition holds in this example. And let me try to make it a little bit bigger. Make the window bigger. There you go. Well, I think it's clear, for, right when you look at it, that this vector field looks like it's spinning. If you were to stick something, especially in the middle, it's very clear that it would spin. But what might be a little unintuitive, you might think, wow, wouldn't something spin faster near the center than it would here? Why is the curl we got is 2. It's a constant. The curl is the same throughout this entire vector field. So you'd be like, well, that's kind of implying that the field is making something spin equally no matter where you are in the field. And let's see if that makes sense. Well, in the middle, it definitely makes sense that something is spinning, right? If I had a little stick here, I'd be pushing in this direction with not that much of a magnitude in that direction, and then I'd be pushing down to the right in this direction, so it would cause it to spin. But what if I had that same stick here, right? You'd say, well, on the top right, I'm pushing up and to the left. On the bottom left, I'm also pushing up and to the left. It wouldn't spin as much, but it would, because the difference in magnitudes of these two, you could almost view them as, the torque producing forces. The difference in magnitude is enough that you would still have the same counterclockwise rotation here as you would have here. So because the curl is a constant positive number, when we look at the xy plane like this, if you put a twig, that same twig anywhere where you put it on this plane, it will have the same counterclockwise rotation. I think that's pretty neat. Now, let's do a little experiment. What would have happened? What would have happened if this was plus y? So let's just do that experiment. If this was plus y, then this would have been plus y, then in this final term we would have taken the partial derivative with respect to y of plus y, and so this would have been 1 minus plus 1, and then our curl would have been 0, which would have meant that we would have had no rotation. And what's the intuition of that? Well, if we just look at it mathematically, if we have 0 curl, somehow the rotation in our x direction must be being offset by our rotation in the y direction, that the torques must be just perfectly offsetting each other. And let's see what happens if I were to change. So this was our old graph. Let me actually change it to my new vector field. So my new vector field. So that's our new vector field. This is the vector field plus yi plus xj. And now the curl is 0 everywhere, which implies, or which means, that I could put a twig anywhere here and I'm not going to get any kind of rotation. Let's see if that makes sense. If I put a twig in the center, or some kind of stick in the center, see, I would have the forces or the fluids pushing in this direction, but they're not helping to rotate, and pushing out in that direction. Well, that's not going to help me either, right? So I'm definitely not going to rotate there. And actually, you could put a twig anywhere, and maybe a twig might be pushed in a direction. For example, if I put a twig here, it's going to be pushed outward by the flow of the water, by the velocity of the water, but it's not going to rotate. So the kind of holds that even though I kind of have curl in the x direction or I have curl in the y direction, they're offsetting each other, so that in 2 dimensions I actually end up having no rotation. And actually this is called an irrotational, I think that's the word, vector field, where you're not going to have any rotation here. All of the, if you think of it as force or velocity of the vector field, is going to be applying translation to objects in that field. And actually, just for fun, let's think about the divergence of that field. Just because I have 2 minutes. So if I were to think about the divergence of that field, since it's fairly easy to calculate, let me erase this real fast. It's always fun to just interpret a vector field to death. Let's do the divergence of this one. So the divergence of that vector field is just the partial derivative of this with respect to x. So div of v is the same thing as our del operator dot our vector field v. And that's the partial derivative of this with respect to x. Well, the partial derivative of y with respect to x is just 0, plus the partial derivative of x with respect to y, right? So this is 0. So the divergence of this field is 0. And even in the other case, when this was a minus, it still would have been 0. And does that make sense? Well, if we take a circle anywhere here, let's take it in the center, because the center is the most interesting. Let's take a circle. So we do have some fluid or particles coming in at a certain velocity from the bottom right and the top left. But just as much is coming out through the top right and the bottom left, right? whatever's coming in through here and here is leaving through there and there. So if I had an infinitesimally small circle or sphere in this vector field, I would have no net density increasing, or nothing would be entering into that circle, or in any given amount of time, the concentration of that circle wouldn't change. And that's true pretty much anywhere. If I were to draw a circle here, because the divergence is 0, it's telling us that whatever is coming in one direction is coming out in the other directions. So I'm not getting any denser or any less dense. I have no divergence or convergence. So that's just interesting. Well, now I've run out of time, so we're done analyzing this vector field. See you in the next video.